everyone, welcome to a new set of video lectures. So far, we've been looking at the linear model as a kind of a mathematical tool, right? To see relationships between variables, maybe their interactions or differences across groups. Now we're going to look at the linear model from a statistical perspective. And we're going to start by introducing and discussing certain assumptions about the data and about the model itself. And by doing so, we are going to be able to see how the coefficients of the model vary or depend on the data we use to fit the model in the first place. And so we're going to go from just looking at the coefficients to kind of quantifying their uncertainty. And by doing so, we're going to see how our inferences from the model, our insights or our conclusions drawn from the model might change once we start doing so. And finally, we're going to see how by changing these assumptions just a little bit, we might be able to study problems of a different nature, such as a response variable that is bounded, say, between 0 and 1 or something like that. Let's take a look. All right, so within the larger scope of the course, we're still going to be focusing on this part about building models and learning from these models. Now, in this block, we're going to, again, talk about the variability in the linear model, about the variability in the coefficients. And we're going to start talking about how that variability might change our conclusions from the model. One of the basic conclusions we might draw, or one of the reasons why we might choose a linear model, is to test hypotheses about differences across groups. So we're going to see how to do that now in the linear model. And we'll go a little bit further into seeing how we can test hypotheses when we have complex models of many different variables, interactions, and whatnot. We'll talk a little bit more about model selection, and we'll finally go and change these assumptions again a little bit to talk about, in particular, logistic regression or logit regression. So let's see, what is it about the variability in the data? Well, let me show you an example. Here we have 4 different data sets about the same phenomena. And we are basically relating a variable x and a variable y. And these are a certain number of observations in 4 different data sets. So what could we say about this? All right, let's start. First, we choose the class of models, right? And in this case, we're going to go basic. We're going to say that the relationship between the response y and the predictor x is just going to be linear. So we have the intercept beta 0 over here. We have the slope beta 1 and a certain amount of error. And so if we actually fit the data, or we actually fit a model to the data, then we're going to have these 4 different cases. In the first data set, then we have this linear model. Beta 0 is negative 2.8 and beta 1 is 0.37. So it's a positive relationship. In the second one, we also have a positive relationship, not that steep. In the third case, we have a somewhat negative relationship. And in the fourth case, we have, again, a positive relationship. And so if we are able to look into all these 4 data sets, then what do you think would be a reasonable estimate for beta 0 and beta 1 in reality of the underlying process behind all this data? Well, if we are able to make a rough estimate, then we could just kind of average the coefficients, right, across the data sets. So we might be inclined to say beta 0 is going to be somewhere around negative 1.5. And for beta 1, we would be inclined to say, well, it's about 0.2, something like that. Well, guess what? In reality, x and y are completely unrelated. They're independent of each other. Y has nothing to do with x. And it just so happened that we were a little bit unlucky in our data, perhaps, to have all these positive and negative relationships. So what the model should have been is beta 0 is 0 and beta 1 is 0. So there's no relationship between them. So what happened here? Well, there's a certain amount of variability, in this case, introduced by epsilon. And this error is going to many times fool us if we just look into the coefficients. We're going to have to start quantifying how much variability we have in those coefficients. And so what does it really mean when a coefficient is 0 or somewhat close to 0? Well, if we're talking about the intercept, about beta 0, then it means that maybe there's no intercept. And then the response is equal to 0 whenever the predictor is 0. So basically the regression line crosses the origin. And so maybe the model is just something simple like that. There's no intercept. What if the slope, beta 1, is very close to 0? What does it mean? Well, it means that maybe y and x are not related after all. So maybe the model looks something like that. There's only an intercept, which in this case would be modeling the average of the response, but there's no relationship with x. And so the point I want to make here is that, well, the magnitude of the coefficient really depends on the units of the variables. So imagine that we have this x that is measured in millimeters. Then the coefficient is going to be 1,000 times larger than if we measure that in meters. And so it's not really about whether the coefficient is close to zero or not, which anyway is something kind of arbitrary. It's about how much the coefficient varies and where does it vary across samples, across different data sets. That's what we want to look into. Where does it vary and how much does it vary? So if we see that a coefficient varies maybe a lot around zero, we might be inclined to say, well, we're not really sure whether this coefficient really should be zero or something different from zero or not. If we see that it doesn't vary too much and it's very far away from zero, then we have kind of strong evidence suggesting that the coefficient is different from zero. So we're going to start looking into these kind of situations from a more principled way through statistical lens.